Hi everyone, today we are going to talk about electromagnetic waves. We are going to start with James Clerk Maxwell. He was a major contributor to physics, not only in what we're going to talk about with today, but also in other areas. So if you're interested, feel free to look him up. He combined knowledge of electricity and magnetism with his own insights into a complete overarching electromagnetic theory, and those are represented as Maxwell's equations. So he has his own set of equations that we'll get into in a second here. And with this, he correctly predicted that visible light consists of electromagnetic waves. And we will talk about something called the electromagnetic spectrum a bit later in the lecture here and talk about these different types of waves. So let's start with his equations. Now they aren't just from him, okay? As you can see, we have Gauss's law, Faraday's law, Gauss's law for magnetism, Ampere-Maxwell law. Basically what he has done is combined all of these into a set of equations, maybe added some corrections here and there. If you're interested in some more details of these, please feel free to look at the textbook. But he got all of these together, and then once all of these fields have been calculated using these equations, we have something else called the Lorentz force equation, which gives us the force that that the field exerts on a particle with a charge q moving with some velocity v. So again, these are Maxwell's equations here, okay? And we'll discuss them a little bit more in detail here in a second. But these are the mathematical representations of these equations. Then we come up with the Lorentz force, which is down here at the bottom. F vector, so force vector, is equal to Q E, which is our electric field, plus QV cross B, our velocity crossed with our magnetic field. Okay, so this is what we have all together with Maxwell's equations. Now let's look at these individually. So here I have listed some key points on these equations. For example, Gauss's law, the electric flux through any closed surface is equal to the electric charge, Qn, enclosed by the surface. So that is the definition of Gauss's law. And this describes the relation between electric charge and electric field it produces. Electric field lines originate from positive charges and terminate on negative charges. So we go from positive to negative, and this indicates the direction of the electric field at each point in space. Okay, so this has everything to do with charges and electric fields. Then we have Gauss's law for magnetism. The magnetic flux through any closed surface is zero. That is again, the definition here. Magnetic field lines are continuous. They don't have a beginning or an end. This is different from our electric field lines as they start from a positive charge and terminate on our negative charges. Magnetic field lines are continuous. Okay, there's no beginning or an end. They are continuous. Any magnetic field line entering the region enclosed by the surface must also leave it. And there are no magnetic monopoles are known to exist. No magnetic monopoles, meaning that magnets are always in dipoles. Okay, remember if we have a magnet, we have a north and a south pole. If we cut that in half, we will just be left with two smaller magnets, okay, and so forth, down to the molecular level. Okay, we learned this in the magnetism section. All right, then we have Faraday's law, which is a changing magnetic field induces an electromotive force, EMF, and therefore an electric field. So this is the idea that if we have a magnetic field, this will induce a force and therefore a field, an electric field, okay? So this is where magnetism and electricity go hand in hand. One will produce the other, okay? In this case, we're looking at Faraday's law. This tells us that a magnetic field will induce an electromotive force, EMF, and an electric field. The direction of the EMF will oppose this change of magnetic field, and the electric field from a changing magnetic field has field lines that form closed loops without beginning or end. Okay. Then we have the Ampere-Maxwell law, where magnetic fields are generated by moving charges or by changing electric fields. So magnetic fields are generated by charges that are moving. So say it has some sort of current involved, and this will create a magnetic field. So this encompasses Ampere's law and adds another source of magnetic fields, namely changing electric fields. Okay, so these are the four equations that Maxwell has kind of brought together. Okay, now one important thing to understand is electromagnetic wave propagation. So how do these waves move? Okay, so let's imagine a time-varying magnetic field that's produced by a high-frequency alternating current. So this is our current. We have an alternating current here, or AC current, and it's producing this magnetic field, B naught. So this is our produced magnetic field. Okay. From Faraday's law, like we just looked at, the changing magnetic field through this surface induces a time-varying electric field at the boundary of that surface. So now we don't just have this magnetic field, but now we have an electric field that is being produced. Okay, so we have this time-varying electric field now. Now, that changing electric field, again, will create a magnetic field according to Ampere's law. So Ampere's law tells us that this E naught, this induced electric field, will now produce a magnetic field, B1. So there's this new magnetic field, B1. Again, this changing magnetic field creates another electric field, E1, here, which produces a magnetic field, and so forth. So you can see that we are just constantly producing one or the other. So let's see, this magnetic field creates an electric field, E1, which produces another magnetic field, B2, and so forth. Okay, now you can see all of these being created along this perpendicular line here, and this is our wave direction. Okay, so this is our wave propagation. Whoops. Okay, so I wanted to quickly talk about Hertz's observation. So we have Heinrich Hertz, who was a German physicist. He was the first to generate and detect certain types of electromagnetic waves in the laboratory. What he did is he used an alternating current RLC, resistor inductor capacitor circuit, that resonates at a known frequency and connected to a loop of wire. These high voltages induced across the gap in a loop, and it produced sparks that were visible evidence of the current in the circuit and helped generate electromagnetic waves. Now I want to show you something in lab, or actually in lecture, I can do that too. Just a quick demo of how we can also produce these sparks. Okay, so it's not going to be what he did exactly, but it's going to be, how we can produce sparks, at least in practice. All right, so let me go ahead and take a quick pause here, and then we will get started again in a moment.